Good evening. We are going to look at induction motor starting in today's lecture. So let me talk about three-phase induction motor starting. So we had told earlier that the three-phase induction motor, while starting, it is going to draw a current which is corresponding to, so let me first start with drawing the equivalent circuit. So let us say the per phase equivalent circuit is somewhat like this. We are going to have V1 applied from the stator side, and this is going to be R1, and this is X1, which are stator side resistance, stator winding resistance and leakage reactance. And we will have a magnetizing reactance, and we will have R2 dash divided by S, which is actually the resistance visualized from the stator side, and it is also taking into account the slip factor, and this is the leakage reactance of the rotor winding, which is visualized from the stator side. So this is the generalized equivalent circuit, per phase equivalent circuit of the induction motor. And in fact, I have neglected core loss component of resistance. So this is going to be the core loss component of resistance, which I may call as RC. So now if we look at it, when we are starting the induction motor, slip is equal to 1 during starting. So what happens during that time is the resistance of the rotor circuit is going to be R2 dash. So R2 dash plus JX2 dash is going to be the impedance of the rotor circuit as visualized from the stator side. And generally the resistance and the leakage reactance are not going to be large values. So they are going to be small values, because of which this particular impedance, what is the impedance offered by this path, it is going to be really, really small. So very, very large rotor current flows through this particular rotor circuit. So this I2 dash plus whatever is the current that is drawn by the magnetizing reactance, which is IM, and this is the core loss component of current, let us say, which is IC. So I'm going to have I2 dash plus IM plus IC. This is going to be the total starting current. So the starting current of the induction motor, if I apply full voltage on the stator side, which is V1, if I try to apply full voltage, the current is going to be enormously high. So what I get as the current, if I want to write, if I write this as I1 starting. So I1 starting approximately can be written as V1 divided by R1 plus R2 dash plus J times X1 plus X2 dash if I am neglecting this portion, whatever I have. This is going to essentially add up further to the current. It's definitely not going to reduce the current any further. So if I write it this way, I can write this as V1 divided by R1 plus R2 dash the whole square plus X1 plus X2 dash the whole square and square root of this. This is what is going to be the current that is experienced by or drawn by the induction motor during starting. And if we look at it, typical values, if R1 and R2 dash, if I try to write in terms of per unit, this may be about 5% of or 10% of the total impedance. That is the voltage drop that takes place in R1 and R2 dash will be generally 10% of V1. The same way, if I try to look at what is the voltage drop that is taking place in X1 and X2 dash, it may be about 20% or 15 to 20% of V1. So what we are going to have is something like this. 1 per unit of voltage is being applied. If I say this is going to be zero point 0.1 whole square, and this is going to be about, let us say, 0.15 whole square, and square root of this. This is what we are going to have as the current that is being drawn. So this will be approximately 1 per unit divided by 0.01 plus 0.0225 square root. If I try to look at it, it will be a very, very large current. It will be anywhere between, like, I may get something like 8 or 10, something like that. So the current that is drawn by the induction motor during starting can be as high as, 8 times the normal or full load current. So I can say the starting current of the induction motor is anywhere between 5 to 8 times the rated current. So the current is going to be so high, whereas if I try to calculate what is the torque, so let me try to calculate the starting torque. So if I try to calculate the starting torque, I am going to have 3I2 square or I2 dash square R2 dash divided by S omega S. This is what is the torque. This is the expression for torque what we derived earlier. So if I try to look at what is the starting torque, so I should say this will be 3I starting the whole square multiplied by R2 dash divided by S is 1 during starting. So divided by omega S. This is going to be TE starting. Whereas if I try to look at what is TE rated or TE full load, that is going to be 3I2 rated. If I just say this is rated current, so I2 rated square multiplied by R2 dash divided by whatever is the slip at full load or rated condition multiplied by omega S. So if I try to look at the ratio of the starting torque to full load torque. So let me write this as TE start divided by TE full load or TE rated. That is going to be 3 and 3 will get cancelled. So I should just write I2 starting divided by I2 rated the whole square multiplied by there is no S here because S is equal to 1 in this particular case, whereas I'm going to get S full load here. So this is the kind of ratio I'm going to have if I try to look at starting torque to full load torque ratio. So this can be as high as 5 to 8 times. So let us say this is about 6 times. So 6 square multiplied by full load slip typically for an induction motor will be at the most 5%, not anything more than that. So this is going to be 0.05. So this is the maximum you are going to have generally. So this is 36 multiplied by 0.05, which comes to about 1.8. Look at this. The current is as high as 6 times, whereas the torque is only about 1.8 times the full load torque during starting condition of an induction motor whose full load slip is as high as 0.05. So if I have a larger full load slip, I'm going to get a higher starting torque as compared to an induction motor which has a lower full load slip. So if the slip of an induction motor is higher, that means we derived this in the last class when we were talking about induction motor. We said that rotor input to rotor copper losses to rotor output or mechanical output. This we derived as if you may recall, rotor input was 3I2 square R2 divided by S. And rotor copper loss was 3I2 square R2. And mechanical output was 3I2 square R2 divided by S. This has to be multiplied by 1 minus S. So we talked about this ratio as 1 is to S is to 1 minus S. So slip plays a very, very vital role in deciding how much is the rotor copper loss. If slip is higher, so if slip is higher, then we are going to have rotor copper loss to be higher. So if rotor copper loss is higher, that means the efficiency of the induction motor is going to be bad. So if full load slip is higher, the running performance of the induction motor or efficiency of the induction motor is going to be not good. But if the full load slip is higher, the starting torque is going to be somewhat higher as compared to another induction motor which may have the full load slip to be lower. So if running performance, full load running performance has to be good for the induction motor, then full load slip should be lower. On the other hand, if full load slip is lower, then starting torque is lower or lesser. So running performance is not as good. Running performance is going to be not that good. So in general, the running performance of the induction motor and the starting performance of the induction motor both cannot be good simultaneously for a given induction motor because they have contradictory requirements. So if I have the running performance to be extremely good, the efficiency of the induction motor is very good. In all probability, I am going to have the starting performance not as good. So that is the reason why there are various methods for improving the starting performance. So methods of improving the starting performance, we are going to look at it now. Or what are all the different starting methods that are used in an induction motor so that the starting performance is somewhat improved. So we said that normally in an induction motor, starting current is going to be really, really high. That is going to be anywhere between 5 to 8 times the full load current. Whereas if I try to look at the starting torque will be only as high as, let us say, 100% to about 180% of T full load. It is not going to be any better than that. So this is one of the problems normally we face in induction motor. So one of the simplest methods of starting induction motor is generally known as direct online starting. That is, you connect the three-phase supply to the induction motor and switch on the power supply, and then you are going to allow the induction motor to start directly. So this is generally known as direct online starting of the induction motor. So we are not going to reduce the voltage. We are going to apply full voltage. So you simply apply full voltage and allow the motor to start directly, which means it is going to take anywhere between 5 to 8 times the full load current, and it is going to have only very limited amount of torque. The torque is not going to be very high at all. So this is allowed only if the starting current drawn is not too high. So this is generally used only in motors which are less than 10 kilowatt rating. If the motor is going to be even greater than 10 kilowatt rating, direct online starting is generally prohibited. It is not allowed by the power systems authorities, because you look at it this way. This is the three-phase supply which is coming from the power grid, and I'm going to connect the induction motor directly to this grid. Okay. Now we might connect other loads also in this point. This is the common point, which is the incoming point, power supply point for my factory. I may have multiple induction motors. I may have many other equipment connected to the same point. So if I'm going to have multiple equipments connected to the same point, and if I am starting an induction motor which is of very high rating, this will draw huge amount of current from here. So what is going to happen is whatever is the impedance of the line. So you can imagine that this the power supply line is having some impedance. So this high current, what is drawn, is going to cause a huge voltage drop in these impedances, the impedances which are inherent to the transmission line or distribution line. So if I connect some load here, this load is going to experience a reduced voltage and it may not function properly. So it can affect all the other loads that are connected to the same transmission line or distribution line adversely, and that is the reason why direct online starting is never allowed for motors which are greater than 10 kilowatt rating. So there are many other starting methods that are used which can reduce the starting current considerably, so that this kind of voltage dip or voltage sag is not experienced by all the loads that are connected to the distribution line or transmission line. So what are all the other methods of starting? And incidentally, any other method of starting is compared with the direct online starting, and we say that the current is reduced by so much factor and the torque is reduced or increased by so much factor. So we always compare, the comparison is always made with respect to direct online starting. So the second method of starting, which I'm going to discuss here, is auto transformer starting, which is very commonly used in many of the laboratories. Whenever we start an induction motor in laboratory, we use this auto transformer starting. In some of the industries, they may have, if this is the transformer that is getting the incoming power supply, we may try to tap a particular amount of voltage, maybe 50% of voltage from the transformer, so that we apply, instead of applying the entire voltage V1, we may apply only V1 divided by 2 to the induction motor. So when we reduce the voltage, the current will also be decreased, and the current is decreased correspondingly, the torque is going to be decreased. Definitely the starting performance in that sense is not improving for sure, but at least very high current that is normally drawn by the induction motor, that is prevented. So in this particular case, if you try to look at it, originally if the current had been V1 by Z, this would have been the starting current originally. Now we are going to have V1 divided by 2Z. This is going to be the induction motor winding current after the transformer. When I use it after the transformer, or I connect the induction motor at the secondary of the transformer after stepping down the voltage. So if I had called this as IST, this will be IST dash, which is actually half IST. So if I say what is the kind of original starting torque, and if I try to compare that with the new value of starting torque, which is TST dash, because the torque is proportional to I square, I am going to have this to be TST divided by 4. So if the current is halved, you are going to see that the torque becomes 1/4. That's what happens in this particular case where we are applying half the voltage. Now this current is IST divided by 2. So if you look at the primary side, this current is going to be halved further because V1 I1 is equal to V2 I2 as far as the transformer is concerned. If I look at it from the primary side, if the power is V1 I1, on the secondary side, it will be V2 I2. So if the voltage has been halved from the primary to secondary side, the current will be halved from the secondary side to the primary side. So what I see as the current here will be IST divided by 4. So I am going to have, if I am going to have the transformer turns ratio as 1:1 by N, if this is going to be the primary to secondary side turns ratio, in that case, I am going to have the current on the primary side, the torque as well as current, the starting torque as well as the current on the primary side. Both are going to be reduced by a factor of 1 by N square. Because we just saw that if I'm going to have a turns ratio of 1:1 by 2, in that case, that starting torque is decreased by a factor of 1 by 4. The same way, the current is also decreased by a factor of 1 by 4. So we generally see that the auto transformer starting definitely decreases the starting torque as well as current. Both are decreased. So in certain applications where I don't require a large amount of starting torque, like for example, a fan load, because in a fan type of load, we are experiencing a load torque which is proportional to speed square. So during starting, the speed is 0. So we are going to have starting torque requirement also to be very, very low because the load torque is going to be very small in this particular case. So the starting torque requirement is low in this particular case. The same way centrifugal pump, which is very, very similar to the fan type load. So centrifugal pump also, we are going to have the starting torque requirement to be low. So in those cases, this kind of auto transformer starting or a transformer with a step down turns ratio, that will work fine because the current will be decreased and the torque will also be decreased quite a bit. So this is one of the starting methods that is commonly used in many of the cases where the starting torque requirement is not too high. The third type of starting that is commonly used again in agricultural pump set. This is very commonly used in agricultural pump sets that are run by the induction motor. In these cases, what we use is something called star delta starting. So in this particular case, what happens is normally the induction motor winding, stator winding is in delta connection. So the stator winding is going to be in delta connection. And what we are going to do is when we want to start this motor, we are going to connect the stator winding in star. So stator winding will be connected in star initially. So what will happen is it is somewhat like this. Let us say I have a delta connected stator winding. So this is the delta connected stator winding. And when I apply the three-phase voltage, I'm going to connect this directly to the three-phase power supply. And let us say I am applying line-to-line voltage, which is corresponding to V. So V line-to-line voltage is being applied here. So if I call this as the impedance as Z, this is also Z and this is also Z. The current that is drawn by the induction motor phase winding is going to be VL divided by Z. So each of them is going to carry an RMS value of current which is corresponding to VL divided by Z. So the line current, what I look at will be √3 times VL divided by Z. So the current that is drawn by the delta connected stator winding will be √3 VL by Z. So this is going to be IDOL. Direct online starting current is going to be as high as √3 VL by Z. Now on the other hand, if I try to connect the same winding in star, so this is going to be the star connected winding, and each of them, again, each of the windings is going to have an impedance of Z. Now what we are doing is to apply the same voltage, which is V line, as the voltage here. Now, if this is the line voltage, voltage that is experienced by each of the phase winding, because this is star connection, will be VL divided by √3. So if I am looking at what kind of current is flowing here, the current is going to be VL divided by √3 Z. So this is going to be the current that is drawn by each of the phase windings. And in star, I'm going to have phase current is equal to line current. Whereas in delta, the phase current is going to be line current divided by √3. So because of this, this is going to be the line current as well when I am looking at the star connected stator winding. So if I connect the stator winding initially in star, I am going to have, as compared to the direct online starting current, the line current in star connection will be 1/3, because this is VL divided by √3 Z, whereas this is √3 times VL Z. So I should say IDOL divided by I star during starting. This is going to be basically having a factor of 3. So we have decreased the current during starting by using the star delta starting. By a factor of 3, we are reducing the current. And what happens to the torque? The torque in star condition will be whatever is the winding current in the star and delta. I have to compare both of them whole square. That is what is going to give me what is the kind of torque that is being generated in star condition vis-a-vis delta condition. So if you look at the winding current here, it is VL divided by Z, whereas here it is going to be VL divided by √3 Z. So I'm going to have this to be 1 by root 3 times whole square as compared to T delta. So if I compare the electromagnetic torque that is developed in delta condition vis-a-vis what is the electromagnetic torque that is generated during star condition, that is having also 1/3 as the ratio. So the star delta starting decreases the starting torque as well as starting current. Starting torque as well as starting line current by a factor of 3. So it is going to decrease to 1/3 for the torque as well as the current. Both are decreased by a factor of 3. So this is like having an auto transformer starting whatever we have seen. If I have 1:1 by root 3 turns ratio in the transformer, that will also give me 1:1 by 3 as far as the current that is drawn from the power supply from the primary side is concerned, and the torque developed is concerned, it is going to be 1/3. So star delta starting is going to emulate the behavior of using an auto transformer with a turns ratio of 1:1 divided by root 3. So if I'm going to have an auto transformer with this kind of a turns ratio, the behavior of this kind of a starter will be very similar to star delta starting. So what is actually done in actual practice is, if I'm going to have these three as the induction motor winding, we are going to have one switch here and one more switch here. So these two switches will be closed during starting. So these are the three-phase power supply that is connected ultimately to the three-phase input. So these are going to be closed during starting. These two switches are going to be closed during starting. These are the A, B, C phases. And if I am calling this as A, let us say C, C1, B, B1, and A, A1. So these are the A, B, C phases. Whereas during running condition, what is going to happen is, let us say these are the three-phase windings, and we had these two switches which will be opened up during running condition, and we will have one switch here which will be closed, and the second switch here which will also be closed during running condition, and this will be the third switch which will also be closed during running condition. So let us say this is R1, this is R2, and this is R3. These three switches will be closed, whereas S1 and S2 will be opened up during running condition. And we are going to have the power supply again from here. This is C, this is B, and this is A. So we are going to connect this to A, B, and C phases respectively. So during starting, S1 and S2 will be closed, and during running, S1, S2 will be opened, and R1, R2, and R3 will be closed. Generally, this will be done after a little bit of time delay. Maybe it will take about 10 seconds or 12 seconds. And after a certain time delay from starting condition, the switches will be opened, and the running switches will be closed, and the induction motor will continue to run further. Because once the induction motor picks up certain speed, it is going to have reduction in the current. Automatically, the current is going to decrease, because we had looked at this, that if you look at the current, it is going to have I2 is going to have R1 plus R2 dash by S will come into picture, but S is going to be 1 during starting. But once it picks up speed automatically, the slip is going to increase. So the rotor resistance will be bloated up because slip is essentially coming to lower and lower value. So the rotor resistance will increase and the current will automatically come down. That's what is going to happen. Okay. So star delta starting is very, very commonly used in agricultural pump sets. Only thing what has to be taken care of is during starting, because the machine is in star situation, star condition, there will be some induced EMF, definitely in the stator as well as rotor. Induced EMF will be there in stator and rotor winding. And when we are actually changing over from star to delta, when we are closing the switch R1 and R2 and R3, if let us say the induced EMF in A phase, B phase and C phase is, like this, they are 120 degrees shifted from each other. By chance, when we close the switch, the applied voltage happens to be exactly in phase opposition. Then what is going to happen is huge amount of voltage will come up across the stator winding itself. And that can actually cause a huge amount of current to be flowing through the induction motor winding, which can be detrimental to the induction motor itself. This can happen because of a large amount of voltage appearing across the induction motor with respect to the induced EMF and the applied voltage. If the two are very different from each other because of the phase shift between them, then you can have a very, very large current flowing through the induction motor, which could be deadly for the induction motor. Okay. So let us now go over to the third method, a fourth method of starting, which we call as part winding starting. So part winding starting actually involves having multiple windings for the induction motor. So I can have, let us say, um, A phase and B phase and C phase. Let me show maybe a star connected winding somewhat like this. So let us say this is the A phase winding, this is the B phase winding, and this is the C phase winding. And I'm going to have normally the voltage applied to A phase, B phase, and C phase winding somewhat like this. Now, when the motor is running in full load, I may have actually one more winding in parallel. Similarly, I can have one more winding in parallel as far as the B phase is concerned. And similarly, one more winding in parallel as far as the C phase is concerned. So this is the way it is. Now I can imagine that there is a switch here, which I will close only during running condition. Similarly, I have a switch here for A phase, which will be closed again only during running condition. Similarly, this is the B phase switch, which will be again closed only during running condition. So let me call this as R1, this as R2, and this as R3. So R1, R2, and R3 will be open during starting. So if I have only one winding put in service during starting, and if I say that the impedance of this particular winding is Z, and this is also the impedance is Z. Similarly, all these things are going to have the impedance as Z. Then we are going to have V phase divided by Z as the current that is taken during starting. Whereas if I try to look at it during running, the impedance is going to be Z by 2. This is the impedance during running. So of course, we are going to have less current flowing through during starting, but during running condition already back EMF has built up. So you are going to have definitely less amount of current again flowing even during running, but a good amount of torque will be generated because both windings are put into service. So you are using only part of the winding for each of the induction motor phases. So that is the reason why this particular method is known as part winding starting. So Z by 2 will be impedance during running, but Z will be the impedance during starting. That is the way it is going to work. So for this, we have to have redundancy in terms of winding arrangement in the induction motor. So you can't say this is very, very commonly used in low capacity induction motor. This is generally used only in high capacity induction motor because you might try to use it with, multiple windings, and whenever you talk about higher torque producing capability for the induction motor, it will require a larger amount of current to be carried. So you may have multiple windings in parallel in any induction motor in those cases. So only in high capacity induction motor, generally part winding starting is used. Another type of starting method that is very commonly used in many of the induction motors is impedance starting. So the impedance starting method is actually something similar to a DC machine. Like in DC machine, we said we need to include a larger armature resistance. The same way what we do is to include an impedance along with A phase, B phase and C phase winding. So this is the A phase winding, this is the B phase winding, and this is going to be the C phase winding, which is star connected induction motor winding I have shown. So this is the induction motor stator winding. And what we have done is to connect an external impedance. So this is Z external per phase. So each of the phases is going to utilize an external impedance here apart from the inherent impedance of the induction motor, which is Z. So we are going to have the current to be, now if per phase voltage is V phase divided by Z plus Z external. This is going to be the starting current that is drawn by the induction motor. So the starting current is decreased based on how much is the external impedance that has been included per phase in the induction motor circuit. Of course, if the starting current decreases, the torque is going to be again proportional to the current square. So automatically the starting torque is also decreased. There is no doubt. But the current is also decreased considerably. Thus, the voltage dip or voltage sag can be eliminated in impedance starting of induction motor. Now, if the impedance is actually having large R and less reactance, in that particular case, we are going to have actually high power losses because I square R losses will be higher. So high power losses will be incurred if I have a larger resistance and less reactance. So efficiency will be affected adversely, will not be good in this particular case. Starting efficiency will not be good in this particular case. Whereas on the other hand, if I have low resistance and high reactance, in this particular case, power factor will be affected adversely. Efficiency may not be affected very badly in this particular case. So you would see that generally impedance starting in many cases may be employed with moderate values of resistance as well as moderate value of reactance, so that neither power factor nor efficiency is affected very adverse. So impedance starting is commonly used again in high capacity induction motors, generally to ensure that the starting current drawn is not extremely large. But of course, starting torque is going to be reduced as well. Very similar to impedance starting is something called soft start, which we again use for many of the induction motors, which want only less amount of many of the load settings where we want only low amount of starting torque. Soft start is actually going to use back-to-back connected thyristor pair like this. So whatever we know as three-phase AC voltage controller, this kind of three-phase AC voltage controller is going to be used along with the three phases of the induction motor. So this is A phase and this is B phase and this is going to be C phase, and each of the phase is going to have one pair of thyristor which are back to back connected. So let us say this is going to be the A phase winding of the induction motor, this is going to be the B phase winding of the induction motor, and this is going to be the C phase winding of the induction motor. Okay, so in that particular case, let us say this is A dash, and let us say this is B dash, and let us say this is C dash. So now if I am applying, I want to apply a low voltage, then the firing angle of the AC voltage controller has to be really large. So when the firing angle is large, less voltage is applied. So when I am actually talking about impedance starting, we said that while starting initially, we have to have a large impedance included in the circuit, external impedance included in the circuit. As the speed increases, this, if it is a variable impedance, I should be able to reduce the value of impedance as the speed increases. So as the speed increases, we are going to reduce the external impedance value will be decreased. That is what we are going to do. The same way here in the soft start, initially we are going to have a large firing angle. Let us say as high as 120 degrees or 110 degrees. Now, as the speed increases, as the speed of the induction motor increases, we are going to decrease the firing angle. So we are going to, the firing angle will be decreased. The firing angle might become from 110 to 90 degrees, 80 degrees, and so on. So firing angle will be decreased. So in this particular case, what is going to happen is, let us say in a particular phase, just A phase voltage, if I am trying to look at, I'm going to see that if it is 120 degrees, I'll apply only this much of voltage in the positive half cycle and this much of voltage in the negative half cycle. On the other hand, so this is alpha equal to 120 degrees. And this is A phase voltage. So if I am trying to reduce the firing angle from 110 to, let us say, something like 60 degrees. So this is going to be 60 degree firing angle and this is going to be again 60 degrees. So this is alpha equal to 60 degree. Now I am applying so much of voltage in the positive half cycle and so much of voltage in the negative half cycle. So as the firing angle decreases, we are going to increase, or rather RMS value of voltage, applied voltage increases. So RMS value of applied voltage increases. So this is definitely going to increase the current supplied to the induction motor. The torque developed by the induction motor is going to increase as the firing angle decreases further and further. But this will serve the purpose of reducing the starting current considerably. So soft start is very, very commonly used in many of the induction motor drives where the capacity of the induction motor is greater than 10 to 15 kilowatt, and the initial starting torque can be still limited. If such an application exists, for that the soft start is very commonly used. Only problem with soft start is you can see that the current, the voltage is not at all sinusoidal when the firing angle is greater than 0 degree. So there will be harmonics. There will be harmonics in the current that is drawn by the induction motor. So if there are harmonics in the current drawn by the induction motor, then definitely it is going to have certain ill effect. We will talk about this as we go along, because this is going to definitely cause a huge amount of vibration in the shaft of the induction motor. So that's not a very good thing. However, soft start is generally used during starting particularly because it's a low cost arrangement. And if you want to ensure that there is no voltage sag, that you don't want to have any voltage sag during starting condition, then soft start is one of the best methods that can be employed. Now, the last but not the least, I'll talk about the final starting method, which is corresponding to wound rotor induction motor. So when you talk about starting of a wound rotor induction motor, in this particular case, if you think about it, wound rotor induction motor, even in the uh, rotor side, it is going to have the three-phase winding. And the stator side is also going to have three-phase winding. Okay. So the stator is applied with normal three-phase supply. Let us say ABC phase supply you're applying to the stator of the induction motor. So this is the stator. And on the rotor side, rather than short circuiting the rotor windings directly, if I include a variable resistance or multiple resistances and short circuit the rotor through these resistances. Let us say I have included this is R11 and this is R22. So I'm going to include two sets of three-phase resistances along with the rotor circuit. Now what will happen is if I try to look at the starting current. So when I look at the starting current of the induction motor, I'm going to have whatever is the voltage that is applied from the stator side per phase divided by R1 plus R2 dash plus R11 dash plus R22 dash. All of them are now included in the total circuit when I calculate the resistance. Then the same way I'm going to have x1 plus x2 dash the whole square. Now square root of this. This is going to be the starting current what I am looking at when I include R11 and R22. Now, once the motor picks up speed, what I'm going to do is to probably close this switch. So I'm going to have some contactors here. This will be closed. This will also be closed. So when I close the switch, these resistance will be eliminated from the induction motor's rotor circuit. So automatically when I calculate the current, I have to remove this particular resistance. So the current can increase now. Similarly, when I talk about further speed increase, I can cut off the resistance R11 also. So I will be able to cut off this also after the speed picks up beyond a particular value. So in that case, I can remove this R11 dash as well. So when I think about the starting current definitely will be decreased. But if I look at the starting torque, please recall what is the starting torque expression. That is going to be 3I2 square or I starting square R2 dash divided by omega S. And now R2 dash is consisting of not only just inherent resistance R2 dash, but it also has R11 and R22 which are included in the rotor circuit. So overall rotor resistance is increased. So the rotor resistance we will be able to increase only in wound rotor induction motor, and it will have an increasing effect on the starting torque as well. So whenever we use a wound rotor induction motor, it has one of the major advantages in terms of modifying the rotor resistance, and modifying the rotor resistance will have two positive effects. One is reducing the starting current itself, and another one is to increase the starting torque. So rotor resistance starting is a very advantageous method of starting an induction motor. But this can be used only in wound rotor induction motor, and we already said that wound rotor induction motor or slip ring induction motor is not maintenance free, because you will have to ensure that the slip ring and brushes are sitting properly, they are making contacts properly. So it is definitely not as maintenance free as that of a cage induction motor. So definitely using a wound rotor induction motor is done very, very rarely, unless you are employing that in an application where you need to reduce the starting current, but simultaneously want to have a good amount of starting torque. So wound rotor induction motors are not commonly employed, but if they are employed only in certain applications where you would like to have a good amount of starting torque and a lower amount of starting current itself. Okay, so these are the various methods of starting an induction motor. We'll try to work out a few problems on starting of induction motor in the next class. Then we will go towards speed control and breaking of a three-phase induction.